In this video, we're going to work a problem involving a pulley with mass. So back in the earlier part of the course, we dealt with a machine called an Atwood machine, where you can have two objects attached with a rope, but they went across. All our pulleys were massless. Now our pulleys are more realistic. They're not massless. They have mass. And what that means is that the tension on one side and the other, if this pulley is picking up speed, then these tensions cannot be equal. Because if they were equal, then they couldn't be changing the speed of this pulley if it has mass. The way to work this problem is you're just got to have to draw a free body diagram from each object that has mass. This block, but you also have to draw one for the pulley now. So the first thing it asks us to do is draw free body diagrams for both blocks and pulley. So there's isolate the objects. There's one mass. There's another mass. And there's a pulley. If I could draw well. Okay, now we have to go through, after we've done that, we have to inventory the forces with 1F. We're going to have a weight, I'll call that W1. There's a weight of the pulley, WP. There's a weight of a block over here, call that W2. Applied. Well, there's no applied forces. Johnny's not pulling on or anything. Normal force. Well, there is this one force here, the axle. Whether you want to call that applied or normal. And that force could be at this direction. It could be at that direction anyway. But any force in two dimensions can be written in terms of its components. So what we're going to do is we're going to place that with two forces. One along the X and one along the Y. The total force of this axle right here is the hypotenuse of those. And if we have the two components, the two sides of the triangle, we can always find the hypotenuse, and we can always find the angle. So I'm going to do that. I'll change color so to make it easy to see that this one is P sub X, or you maybe want to call it A sub X. I like to call it P for pivot. That's its X component, and it has some Y component. And we don't know what those components are. Those are unknowns we'll have to find. We also have tension. We have two ropes in the problem. This block here is pulled up. We'll call that T1. It is pulled up by that pulley. That pulley has mass now, so that's what's pulling on it, not this other block. So if the pulley pulls up, then the block pulls down on the pulley. We also have a tension on this block pulling up, T2 we'll call it, but that's being pulled up by the pulley right here. So that means it's pulling down on the pulley, T2. And there's no friction. So we've inventoried all the forces with 1F. Now, we need to have some axes. This axis here I'll call X and I'll call Y. And by the rule of the gun, if this block goes up this way in the Y direction, this block goes down in the Y direction. So we need to rotate our axis to show that. So by the rule of the gun, I rotate the axis. So this is Y and this is X. If you don't remember the rule of the gun, you need to go back to the earlier videos that we did back in the earlier part of the chapters on rotation, way back in chapter 5. For this pulley, we don't rotate the axis on this pulley or anything, and the reason is that this pulley is not moving up and down or right and left when these two blocks move. All it does is rotate. That's what we need to connect to the motion of this object. So we're going to draw here a coordinate system. You can draw it to the side or you can draw it up, whichever way you want. I'll draw it to the side here. And here's an important thing. You need to link its motion. So when this object goes up and this object goes down and accelerates in the Y, this point on the rim, which is touching that rope moves up. If this pulley does not slip, if that string doesn't slide across it, so we're assuming that it's rolling without slipping, then this pulley will rotate around in this direction. To connect that motion, we need to make the direction of positive acceleration and positive torque to be like this. So that when this moves, this rotates, this falls. They have to be linked. If they're not linked this way, if you make this go the opposite direction, you're going to have to put a minus sign when you try to link in the angular acceleration of the pulley to the tangential acceleration to the point on the rim to the tangential acceleration of this rope, and trying to connect those. This eliminates all of that. It just enables you to make this point, this turns this away, this thing falls. So it makes it a lot easier. Now, last but not least, we got an axis. We also have to have critical angles and dimensions. There are no angles needed here to break up these vectors. There are no angles here needed to break up these vectors. There are no angles here needed to break up the vectors, but we need critical dimensions to calculate torques. And the critical dimension we need is the radius of this pulley. So we need to put that in this problem. So we need to mark that that is R, so that we have the moment arms for calculating the torques. That's a proper free body diagram. Now what we're going to do is read that free body diagram and apply Newton's laws to work this problem. Might want to write some things down. Big M is 0.51 kilograms. Little m, 0.42 kilograms. Mass of pulley is 0.31 kilograms. R is 6 by 10 to the minus 2 meters. Those are the things that we need to know in order to calculate stuff later in the problem. All right, let's go to the next question they ask us on this. What is the magnitude of the block's acceleration? This is actually going to take several steps. It starts with us writing the sum of the forces in y is equal to the mass of the little block times acceleration in y. And then we have to actually read that acceleration. We have T1 pulling up minus W1 pulling down, and that's equal to MAY. Well, my problem is that I don't know T1. I know M1G here, that's okay, and I'm trying to find A1, so while that equation is good, that equation will not solve the problem. For the second block, the sum of the forces in y is equal to big MAY, and in that case I have W2 minus T2 is equal to big MAY. And that's what we did in the first time we hit pulleys, but what was different is because the pulleys had no mass, T1 and T2 were the same, and we just added these two together to eliminate the T's. We can't do that here. This T1 is different than that T2. So we have two equations, but we have 1, 2, 3 unknowns. We need another equation. Where are we going to get that other equation from? We're going to get it from the torque equation for the pulley. The sum of the torques about the center of the pulley is equal to the moment of inertia of the pulley times its angular acceleration. Well, what type of torques do we have? Well, let's see. Turning the pulley in the wrong direction, or the backward direction, negative direction, is minus T1 times R. Let me move up and show you that. Certainly you have it on your paper. But what I'm saying is that the torque is this force. It's perpendicular. Remember, strings always come off perpendicular to the radius of the pulley. And this R for the moment arm. And that force is attempting to turn this pulley this way, which is in the minus direction because it's opposite my arrow. We also have T2 here. So let's go up and put that plus T2 times R. And that's because this one's pulling here and it's at a distance at R. PX, PY, and WP, the weight of the pulley, are all at the center They provide no torque about the axle, so they don't show up in the equations. This is equal to the moment of inertia. Now I get that from my table figure 821 in Giancoli, or equivalent table. That's 1/2 the mass of the pulley times the radius squared. That's the moment of inertia, and then that's multiplied by the angular acceleration. So that gives me 3. Now let me simplify this guy a little bit. It's obviously that I can cancel an R. So let me do that. I want to cancel that R, and that. I also have the no slip condition. No slip condition. The no slip condition says that the tangential velocity of the rim of the wheel is the same as the rope. Well, the rope is AY. The rim's tangential acceleration is R alpha. So this R times this alpha becomes AY. And this becomes minus T1 plus T2 is equal to MP over 2 times AY, where I've simply taken and eliminated that with the no slip condition. So I have three equations. This equation, and that equation, which I can now add together to get my unknown solved. So if I do that, add 1, 2, and 3, we get, well, T1 and minus T1 cancel. Minus T2 and T2 cancel. So I get W2 minus W1 is equal to M plus big M plus MP over 2 times AY, or AY is big M minus little m times G. All of that divided by little m plus big M plus MP over 2. Notice what happens. This looks like the net force. This looks like the equivalent of a net mass. But the pulley's mass is only half. That's because of its geometry. And I still get acceleration. So still F equal ma. These are the external forces. The internal forces, the tensions, fell out of the problem. Putting this in, we have to get all our values here. So I go back up and remind myself what those values are. Meters per second squared. And that's the answer to this part of the problem. All right, we'll see you on another video.